Another CTF video. What else did you expect? So I haven't done any picoCTF challenges on the channel for a while, so I figured why not dive back in and showcase another one. So today we'll be looking at Classic Crackme OX 100. It is a medium difficulty reverse engineering challenge from picoCTF 2024, and there's even a tag here saying that you can do this completely within the built-in browser web shell. I don't personally use it, but we can see here, I think I need to zoom out a little bit. I don't know, you can barely see it right here in the corner. I don't know why it's not like populating correctly. Here we go. So we do have a web shell, and we can log in with our username and password here, and it just gives us access to that shell, that training environment within picoCTF. So if you don't have access to a Linux terminal or a Windows terminal and you want to solve everything in the web shell, you can. I know people like to do that, or maybe they're forced to do it if they're in class. So let's open up the challenge. It says a note here: binaries downloaded prior to the 13th of March may not match the intended solution. Please re-download if you need to. The description reads, this is a classic Crackme. Find the password, get the flag. The binary can be downloaded here. So let's grab that link, crack the binary file locally, and recover the password. Use the same password on the server to get the flag. So we can launch it now, but let's just wait. We don't have the password yet. So I do already have this binary downloaded and installed. You will have to do a chmod plus X to make it executable, because it won't be marked executable when you download it. So if I run the file command on it, we can see it's 64-bit binary. Okay, it's dynamically linked, meaning any of the shared libraries and objects it needs aren't in the binary, but it'll be pulling it from other libraries, and it gives one here, for example. Let's see. Okay, we get the Linux kernel version, and it has debug info. It's not stripped. That's neat. I've never seen this comment with debug info, but I have seen not stripped before. So that's awesome. Let's do LDD on Crackme just to see what kind of shared objects and library it's using. So it is using the C standard library and whatever this is. I think this is the linker or the loader. I don't know, but we know it's using the C standard library, so it'll have access to printf and putstring and memcopy and maybe string compare and all stuff like that. So let's actually run it and see what is going on. Make sure that's nice and big for everyone to just see. So it asks us to enter a password. I just like putting in my password of please subscribe, and then it prints out in all capital letters that we failed. I'm going to minimize this just so we can see my background. Let me know if you know what video game that this is from right here. Sweet. So we ran the program. It asks for a password, and then it prints out failed because we didn't enter the correct password. We could see if there's like some type of buffer overflow, but this is a reverse engineering challenge. It's not like a pwn or binary exploitation kind of challenge. So they probably don't have any type of buffer overflow that they want us to exploit. Let's look at the strings, because that can be helpful. Let's pipe that into less, because it can be a lot of information. We've already seen this library object. We see some function calls that we're familiar with. Put string to print out text to the screen. Strlane, so it's checking for the length of the string. So it's probably looking for the length of whatever we entered. We see the standard out file descriptor. We see memcopy. So normally these Crackme functions, or these Crackme binaries, they have a call to string compare. So compare two forms of user input, really. So compare what we entered. In this case, I entered please subscribe. Compare that with the actual password, which is usually hard coded. But in this case, they're using memcompare. Or at least that's what I'm thinking. We will look at it in more detail later on, and I'll do a deep dive into memcompare if it comes back up and if we need to. So we see a call to printf, not very interesting. So we're scrolling down here. Oh, okay, we see enter the secret password, and then we see this %50s. So if you've ever used print string before, or not print string, printf, the F stands for formatted. So you need to specify some type of format string, usually %D for decimal, %S to say I want to print out a string or like a character string. But what does this mean? What does the 50 mean? So we're used to %S. Cool, we see that here. So we see success, here's your flag, and %S. So the %S is a placeholder saying it's expecting a character buffer or like a string after, but you can also add a width or a length. So it's expecting 50 characters maybe. So it comes right after enter secret password. So maybe your password has to be 50 bytes in length, which maybe that makes sense because we did see this call to Sterling or string length. So maybe at some point it's checking if our user input is 50 characters long, if I had to guess. Then we see some variable data types, integer and size type. Maybe this is how the binary was compiled. So machine architecture, x64, G to specify the debugging info, no pi, no position independent executable. So don't make it randomize addresses. So don't have static addresses, don't randomize them. Let's see, protection none. So I think this means no like stack canaries, and I have no idea what asynchronous unwind tables is. Then we see some other stuff, some macros. We see memcompare again, printf. Oh, I saw something. We see secret 1, 2, and 3. That's interesting. So there are some type of secrets going on. I did overlook this. This is a sample flag. Okay, who cares? So there's 3 secrets, and there's 2 randoms. Random 1, random 2. I don't know if these are variables or if these are functions. Probably function calls. We see function main. Okay. Is there anything else? We see some of the header files. It's including something called /challenge, main sample. Okay. I don't think there'll be anything else useful in here. But it's always good to kind of look through the strings. At least I like to. You could always just dive right into reverse engineering. But before I throw anything into like a decompiler or a disassembler like Ghidra or IDA Pro, I personally just like to gain a little bit of understanding in the terminal. Maybe you don't want to do that for a huge file, or if it's something like malware that you're analyzing. Maybe you'll just... If it's a big project like that, maybe you just throw it in Ghidra or IDA right away. But since these are small standalone binaries, I really don't mind just taking my time poking through in the terminal. So next, what can we do? We've already ran it normally, but let's run it and inspect it with straced so we can look at some of the system calls that's going on. So we see a lot of text being printed to the screen. Let's zoom out a little bit. So... let me exit this. I don't think that ran the way I wanted it to. ls, strace, Crackme. Okay, that looks a lot better. So whenever you run strace on a binary, it's always going to start with like the same kind of preamble. We're seeing exec_ve being called. Exec_ve is just a way to run, I guess, commands. It's very similar to system. So it's just running Crackme. We don't really have any arguments we're passing to it. It's doing some memory mapping. So it's actually loading this into virtual memory. And we see here, we see this call to write. Let's make that big enough for everyone to see. I don't think it likes it when I do that. When I zoom in and use my mouse wheel. I think it's kind of breaking it. 3rd time's the charm. So we see this call to write. So write 1, so write to standard output, enter the secret password, and then it returns 27 because that's how many bytes it has written. And now it's reading and it's just hanging. It's waiting for us to enter something. Let's just enter whatever. And it fails. It prints out failed. Let's do the same exact process, but this time using ltrace. So strace will look at the system calls, read, write, execve. ltrace will look at the library calls, so the functions that are defined in like the C standard library, for example. So we see a call to printf. So it prints the same exact thing. It returns 27. And we see scanf. Scanf reads user input into some type of buffer. So we can see one of these is the buffer 0. So it's just waiting. Enter whatever garbage we have to. There we go. So we see a call to Sterling. So it's comparing, or it's getting the length of our string. Oh, this isn't our string. This is something else. We didn't enter this. So is this the hard-coded password? It returns 50. And then it's doing mem compare on these two addresses and 50. And then it prints out failed. Let's look up the man page for mem compare. What's going on here? So we can see it takes 3 arguments. 2 of these are addresses or pointers. And then it takes a size. So mem compare function compares the first n bytes, each interpreted as an unsigned character, so a positive value, of the memory areas S1 and S2. So it's comparing the first 50 bytes of these values. So what is this? Let's open up Python. Length of that. Is this 50 bytes? No, that's only 32. Help me. So maybe it's being cut off. Let's open this up in GDB. Crackme. Let's disassemble main. No simple table loaded use file. There we go. I don't know why I didn't correctly load the simple tables. So main is pretty beefy. This is a lot of lines of text. So these are some weird values being passed into these registers. That's kind of fun. But what I really am interested in is that call to mem compare. Let's find that. So here it is, all the way down here. So all the way down here is where it does mem compare, and then it'll probably print out pass or fail down here. So if I grab these values, examine a string this, so this prints out the flag. So if we get here, we know we won. What does this do? What is this printing out? Failed. So if we get here, we know we failed. However, if we're up here, then we know that we have passed. Yeah, so this is the success branch, I guess, and then this is the failed branch. So if we win, it'll print out the flag, and then it goes to main plus 541, which is down here, which just sets the return value as 0, and then it exits. Cool. So here's the call to mem compare, and we see these are the 2 buffers being compared, the 2 values. However, so this is pretty small. Like right here, that's not a lot of lines of assembly. However, if we scroll up, we see there's a lot going on here. So it's probably doing some type of like arithmetic. We see a lot of shifting right, and we see moving and subtracting and adding and multiplying. So whatever we enter, it is doing some type of encryption, I guess, for lack of a better term on it. We see that call to Sterling. Let me break here. Let me break on this call to string length. So break star, slam that address, run it, enter your password. Let's just do ABCD 1 2 3 4. Okay. I'm using GDB enhanced framework, so it will print out the registers for us. So it's calling stir length on whatever is in the register RDI. What's in RDI? So it's this address, and it points to this. So is this 50 bytes? Like we saw this in our ltrace output, but some of it was cut off. If I grab this and open up Python again, just look at the length of it. So it is 50. So if I enter this, what is this? What is this hard-coded value? Let's hit next instruction. We're just stepping through. We know the return value will be 50. So if we look at EAX, we should see 50. Yeah, OX32 and hex is 50 in decimal. Let's disassemble this. So we don't really care, or I shouldn't say we don't care about it. We're not going to reverse engineer all this math right now. Let's set a breakpoint here on this call to memcompare. C to continue. Now look at our stack. There's a bunch of crazy stuff. So I don't know if this is the encoded or decoded value, but the two registers are RDI and RSI. Those are the addresses that are being compared. So if we scroll up here and we look at RDI and RSI, so RSI still has that weird value we saw before, that weird hard-coded sequence of characters. And then RDI is probably our user input that got all mangled up. And we see it's also 50 characters. We can see just by looking at it that these are the same length. And if we just keep hitting next instruction, it's testing to see if these are equal. Hit next instruction again. And we see RAX is not 0. I think that value is -1. Oh, I actually have no idea what it is. And hex. Let's set register RAX 0. I forgot to do this in GDB. So this is just so we take the successful branch. No, I did it wrong. That's okay. So now let's rerun the program and let's throw in this hard-coded value. Let's see if that changes anything at all. So run. Let's slam in this hard-coded value as our password. We're gonna hit C to continue because we care about this. Okay, so this is RSI right here, RSI. That has the hard-coded value from before. And then this is our input that was like encrypted or mutated. So if we really wanted, we could look through these instructions in GDB, disassemble. So it's doing some type of mathematical operation. We did see calls to secret 1, 2, and 3. However, I don't see those functions being called here. There aren't really many external functions being called. Let's just do a quick disassemble of secret. I'm gonna hit tab. So these are functions, I guess. They're there. We also saw random 1. Okay. We could step through one by one and look at all of these and see how exactly it's being mutated. But for stuff like this, it might just be easier to exit out, cut our losses, and then open this up in Ghidra. So just run the Ghidra command. You might have to install this. I don't think it comes by default on Kali Linux. I'm not sure if it does anymore or if it ever has. So I have this open from a last video, I guess, a last project. Let's do, I need to make a new one. File, new project, not shared, just me. Oh, this is back when I was still doing clonable.kr videos. So let's change this to our current working directory. We want this to be picoCTF. And Crackme. There we go. So now we just have to click on this little dragon icon here, and that'll open up the code browser. Alternatively, you can open up a debugger or an emulator. I'm not sure how much we'll actually need to debug. I think what we want to do is just decompile, meaning we want to turn that assembly code we saw into some type of like C pseudocode. So I'm gonna click on File and then Import, and we're just gonna load in our binary. I need to get to the correct directory, YouTube, picoCTF, Crackme. Here we go. Yep, that looks good to me. It hasn't been analyzed yet. We can say yes. This shouldn't take too long. It's going to print out a bunch of information that we already know because we looked at it earlier. I like looking at it manually, but if you want to just do it in Ghidra, that's fine as well. So it does load us right in the main function, and we can start seeing some variables and whatnot being allocated. So I double clicked on main and we can see it opened up here in this tab. Hopefully I'm not in the way. So I'm going to close this strings tab and now we can just look at this here. Let's see if I can make this any easier to read. Let's see how I make the font bigger. There we go. Font 20. Apply. Let's actually, let's just make it bigger. Font 28. Okay, hopefully that's easier for you guys to read now. So we have the main function. We see some variables being declared. It doesn't really know what to call it, so it just gives them generic names like variable1 and local. But we see there's a buffer here. We see these hard-coded hex values being created. We see the printf, enter your function, or enter the password. So local A8. So this is the buffer. Let's rename it. So this is the buffer our user input will be stored in. And I am horrible at naming variables. Let's just call this password buff for password buffer. So it's calling Sterling on local 68. We know local 68 now is that like hard-coded value, I guess, or this is an address. So let's rename this one length. This probably isn't the right thing to call it, but for now, let's just call it hard-coded password. I know that's incorrect. Okay, so it's casting the length to an integer. Okay, so now it's creating these 4 bytes, 55, 33, F, and A. So now there's a for loop. We can see here local C is being set to 0. So I'm going to rename this I for index. So it runs 3 times. Another for loop. Let's call this one J. Keep hitting the wrong buttons. L. Let's call this J. So it's grabbing the characters in our password buffer and it's performing like subtraction and addition. Is it using these? Local 20, local 21. So what are these? What are these hard-coded values being used for? Where's local 28 defined? Local 28 is the result of this operation. And then it calls memcompare. So this is the crux of it right here. We need to figure out what this for loop is doing. I'm going to rename these. This probably isn't good, but I'm just call this hex 55. And I'm going to call this hex 33. Hex 0F. Because I don't think these ever get reassigned. Hex A, I guess. So right now, I just want to rename everything just to get a good understanding of what is going on. So local 28 is the result of this. What was a good name for this? And I'll show you why I'm naming all this in a second. Retval1, and let's call this Retval2. Name this Retval3. I know guys, it's pretty bad. Pretty horrible naming. I wonder if I can just grab this, copy, paste it, and throw it inside of, you know, text editor, compile it. Something I am kind of worried about, I don't see these characters being defined at all. You know what? Let's see. Let's grab this, copy it, and let's throw it in REX2. Tag capital S, slam it in, right click, copy. Is it little s? Yeah, okay. So remember that hard-coded value that we saw before? This one? Let's do this here. This looks like part of that, right? It's in reverse, KGXMW PB. So I guess it's split up in chunks for some reason. Oops, what am I copying? REX2 tag S. Grab this. Yeah, so this is that hard-coded string. So this is just the beginning of it. This is like part 1 and part 2 and so on and so forth. So let's, I guess we could do this in Python. I kind of want to do it in C though. So I can rename this password piece 1, and this is password piece 2, and so on and so forth. So these are the different pieces of the password in hex, not in ASCII. I wonder if I just grab all of this and copy it. I could throw it inside of Python. It's already in C pseudocode. Let's open this up in Sublime Text. What should I name it? Call it solve.c. Make that nice and big. Slam it in. Now, if we try to run this, it won't work. We need to actually add in the correct library code. So include stdio.h, include string.h. And then we might need a cdlib. Let's change this from undefined to int. And it won't let us leave these as undefined 8. I think these are longs. Long. How do I find and replace? Find all. I don't really use Sublime. And I don't think we need this, so I'm gonna comment this out. We don't really care about setting the virtual buffer. I could probably take out a lot of this, but I'll leave it for now. First, let's see if it even compiles. Save, go to our interpreter. And if I do strings on Crackme and then grep, I don't know, protect. That's not the name of the file. Grep protect. So we do see how it was compiled. We see the version of GCC, I believe. So we could use this as well. But let's see if we can do it on our own. Solve.c. Where is that used? Did I miss something? Oh, it's right here. So let's rename this password piece 7. And I might get rid of all of this and just paste in that hard-coded password. And then there's something called dat that I did not like. So this is standard input. So now let's go to compile it. Awesome, so that works. It gives us a little warning. We can change that and take off this ISO C99. Scanf. It might need the address of password buffer. Let's look at the man page for scanf. See that ISO C99 again. Okay, so I poked back over here in the code browser and I double clicked on dat. I guess that's the data section for this address, 402024. And we do see over here, I know it might be kind of small, but this is the %50s. So I'm confusing, maybe I'm confusing it with fgetS, formatted get string, but we don't want standard input here. We want to specify that we want to read in 50 bytes. And then this should look good. So now let's up arrow compile, and it works with no issue. It'll be a.out. Enter the password, hello world, and we get failed. So awesome. So we did reverse engineer and decompile this binary. And if we really wanted to, let's rerun that strings command and let's see if we can compile it, specify, I'm calling it solve. Maybe that's not the best name. Let's add these compiler flags and see if they work with our version of GCC. Some of these did not. Do an ls. Move it out. Let's only include the flags we know we need. Let's take out that. Cool. So cool, we have our own version of this binary. Let's add some print statements. %s new line. Compile and rerun it. ABCD. So that's what it is doing. Do we still have that hard-coded password? Let's grab that. Plug that in there. So it is changing it. I'm not sure what this is at the end. Do I still have my GDB session? Because here we looked at what it should look like, right? It should look something like this. So it's getting up to here. I'm not sure what this garbage at the end is. Maybe it doesn't matter. So I'm gonna grab this final value. Just that right there. Now rerun it and slam that in as the password. Let's run the normal Crackme 100. Okay, whenever you're stuck, like I kind of am here, it's good to just add some print statements just to verify our assumptions. So let's print out the length. Let's see if we are actually reading in 50 bytes. So recompile this and run it. ABCD, length 12. Okay, so that's one issue with it there, but it's still printing out success. Why did it give us success all of a sudden? I took out that len. I took out this. I'm not sure why it's casting it to an integer. Let me throw this back in. Save it. Recompile. Run it. ABC 1 2 3. Length 14 prints out that and it fails. Okay, so it's not reading in the full 50 bytes. Because remember when we did ltrace and Crackme 100, we enter whatever for a password. We can see that it's doing stir length on that hard-coded value and it's returning 50. So let's come back here. I think having this in these individual hex values like this is throwing it off. It's only checking the length of that first password piece. It's not checking the length of the entire password. So here's what I will try next. Let me grab this hard-coded password, this ASCII, and let me declare a buffer here. PW was this. Let's comment out all of that. Well, it won't like that because I think it's... Where's it using these password pieces? Let's see. And let's comment this out. Let's change this up a bit. Address of PW. Address of password buff. Let's print this out. Okay, so we didn't really change too much. Instead of using these individual password pieces, we just placed the entire ASCII here. I do need a semicolon. We took out this stir length check and made our own. It'll print out the length. It'll do whatever mathematical operations it's doing here. And then it prints out password buff and password. So password buff is our user input, and then this hard-coded stuff. And then it's calling memcompare. Let's run this. ABC 1 2 3. Sterling is 50. Here's our encoded input, and here's the actual password. Okay, so this is the main crux. This is what's causing us the most hassle, the most issues here. We have this for loop, and it's two for loops, right? It's nested for loops. This one that has J, it goes over the entire length. Make sure I can zoom in so you guys can see it. It goes over length, which would be 50. So for every single character in our user input, it's going to do this kind of mathematical operation, right? It's going to take the current character, which would begin with a K or whatever we enter, do mod FF, shift it over by 1, and it with these hex values. And it's a lot. So if we want to solve it, we need to do the inverse of this. And I think it's going to be a little bit ugly. Let me remove these password pieces. I really don't think we need them. So what I'm going to do is just highlight and copy this code. And we're going to ask our good friend Claude AI if they can lend us an assist and help us create the opposite of that encoding function, right? So we already have the encoding function that we decompiled with Ghidra. Let's see if we can make the inverse of that. So let's give Claude a nice prompt. Okay, so I've entered a prompt inside Claude AI. It just simply states, hey, I have a C program that takes a password as user input and encodes it using nested for loops. The user input is expected to be 50 bytes long. Let me fix that typo. I will give you the source code. Please help me create a snippet of code to decode the password string. So let's do these 3 backticks. Hit Shift Enter, and that will open up a code block for us where we can paste in what we have decompiled so far. And let's just hit Enter, and let's see what Claude AI can come up with. And it is being a little bit laggy and slow. So to decode the password string, we need to reverse the encoding process implemented in the given C program. Here's a snippet of code that should decode the encoded password. So it created a C function called void decode password, and it will take our encoded password and a length. We see those same hard-coded values that we saw before that we defined ourselves, and it should just be doing the opposite. We can see now it's going backwards. It's saying j equals length minus 1. So start at the 49th character, so the very end, the last character. And while you're greater than 0, so just do this stuff in reverse. Let's look at the encoded one. Interesting. I'm curious if this will work. And then it even tells us how we can use it. So to use this decoding function, you'll call it like this. So take that hard-coded password and get the string length, and then decode it. The coding function works by reversing the 3 steps in the coding process. It iterates the same number of times, which is 3. So it encodes it 3 times or decodes it 3 times. For every iteration, it processes the characters in reverse order. It reconstructs the intermediate values, return value 1 and 2, using the same formulas, and then it reverses the final step of the coding to get back to the original code. So note that this decoding process modifies the input string in place, so the original encoded password will be overwritten. So cool. Let's see if we can just grab this, copy it. We'll go to Sublime, and let's find a good place to chuck this. So we wanted to find this outside of main. Tab this over. We don't need this defined twice. Clean this up a little bit. Okay, so let's look this over real quick. So we have our encoded password that's the same. We have the string length of this. So this should be 50. And then decode password, print the decoded one. And we don't need that. Control S, recompile. I know this is getting sloppy. Ooh, it doesn't like any of these. So we didn't need any of those variables, so delete those. Let's see if we recompile. Line 7, it doesn't like this. Yeah, let's just get rid of this. This looks horribly ugly. No, that can't be right. Oh, wow, that worked. Awesome. So that was very sloppy. However, so we still had all that decompiled code in Ghidra. So I removed a good chunk of that from our Sublime text. And now this will just have the function decode password that we got graciously from Claude AI. And then our main function is a lot smaller. Actually, we don't even need these declarations just to clean it up a little bit more. So we have our encoded password. We're getting the length of it. And we call decode password, which just does the reverse of the encoding, and then it prints it out. So we compiled it and we ran it. And it printed out this very ugly sequence of characters, and we fed that to the original Crackme program, and it printed out the sample flag. So we know this works. So let's come over here to picoCTF. And this is stuff from Rob Emporium. So picoCTF, Classic Crackme, and let's actually launch this challenge instance now. So we can connect to the server, and hopefully it's that same password that we just cracked. So we can connect here with netcat on this hostname import. So grab this, move it over, enter the password. Let's see if we can use that same decoded password. And it works. We get our flag, picoCTF, solve angry symbols. Grab this, slam it in, submit. Nice. So we did solve that challenge. We didn't manually sit here and reverse it, or we did reverse engineer it, but we didn't create the inverse decoding function. And I don't really think you have to. If you want to, if you like stuff like that, if you like cryptography and you like encoding and decoding, you could have done this. But for people like me who, I don't know, we have tools like this. OpenAI has ChatGPT, and then this service has Claude AI. I'm not saying have this solve the challenge for you or do everything for you, but we did reverse engineer the binary. We did have a very good understanding of what was going on. I was just fumbling and tripping over how to create the decode function, and I don't want to sit here another 30-40 minutes trying to figure it out. So for that, I think that is 100% fine, throwing it in AI and having AI help you. I don't really see it being any different than using a decompiler. They're just tools, and tools are there to help you. So if you want to be super hardcore, you don't have to use any decompiler at all. You can just look through all the assembly in GDB and just try to figure it out that way. However, things like decompilers were created to help you save time and mental energy. It would take a lot of mental energy to just look through and pour over all of this assembly and try to understand it. So when you can, using decomplers is awesome. And then taking that to the next step, when you can, using tools like AI to help make decode functions or help do little things like that, it just saves time, man. I think it's awesome, and it even gives you an explanation. So as long as you're understanding what it's saying, I personally don't really see any problem in using AI code. It's just a tool. And tools are there to help you, the reverse engineer, the hacker, the programmer. So that's really it for that. Kind of a long video. I did solve this blind. You know, I haven't done this before and then re-recorded it. So there was a lot of pitfalls. There was a lot of stumbling. You know, this wasn't the prettiest code. However, hopefully you guys gained some insight from this. I know you guys want to see more reverse engineering videos in the process of that. So let me know in the comments below if you guys found a different or better way to solve this challenge. Link in the description if you want to buy comfortable hacking merchandise like this. As always, take it easy and see you guys in the next video.